couple of announcements before we get started today. Project 3 is due Tuesday, next Tuesday. And then homework 4 will be out later this week, due next Friday. And then just another reminder that the midterm is coming up. It'll be a week from Tuesday. Right, so last time we were talking about Bayes nets. And Bayes nets, we were saying, this is a really nice, really compact model for expressing really potentially large probability distributions that are joint over a bunch of different random variables. So we got through all the syntax and all the semantics of how do these Bayes nets work, how do we make them, how do we construct them from our joint distributions. Now we want to ask them questions. We want to have them help us to understand the world. So this is a Bayes net that's looking out the window and telling us whether there's traffic based on some different variables. Yeah, so just a little bit of a refresher. A Bayes net is a graph, and it's a collection of conditional probability tables. So the graph tells us the structure. It tells us which variables depend on which other variables, which ones are conditionally independent from which other ones. And the structure is encoded in this graph. And then for each node in the graph, that'll be corresponding to a particular variable in this joint distribution. And it will be associated with a conditional probability table where the conditioning variables are the parents in the graph. So then when we want to get the joint distribution, we just multiply all of these conditional probability tables together, and we get this sort of thing where each one of them is conditioned on the parents, and then we have this product of all the different conditional probability distributions. And because of the conditional independence assumptions that are baked into the structure of the Bayes net, we're going to recover the full joint distribution, even though we didn't sort of keep track of necessarily the entire chain rule that we would have had to do without those conditional independence assumptions. Right, so that's Bayes nets. And now we want to do inference. Inference is this idea of how do I infer something about the world given my model of the world? And that could take a number of different forms, but an example is, I have some query variable that's in my joint distribution that my Bayes net can help me to predict given some evidence variables that I'm going to set in a particular way. So, this could be like evidence in a courtroom trial. You want to figure out what's the probability that the defendant is guilty, considering all of the different pieces of evidence that they've got stacked up against them. It could be, I could have like a spam filter that I'm designing, and I want to send my email through this spam filter, and I want the spam filter to predict the probability that the message contains spam, given that it has these features in it, right? It contains these words, it's this long, it contains, it comes from this particular shady email address, it has these particular sketchy links that I probably shouldn't click on, it has these attachments. Like, is it spam or is it not spam, given all of those features? So we put the evidence into the model, and then you want to get this probability distribution of the query variable to come out. And similarly, we can also ask for the most likely explanation given some evidence. So if we have a distribution, we have all these different possible values that the query variable can take on, and we want to know which value maximizes the probability given the evidence that we've seen. So these are two examples of how we would, or why we would want to do inference. And we've talked about this a few times now. There's one sort of easy way that will always work, but of how we can get sort of answers out of our probability models, right? So in the general case, we have k different evidence variables. We have some query variable. It could be multiple query variables, like maybe we want the joint distribution over like Pac-Man's location and the number of dots that remain conditioned on some other evidence. So this could be multiple variables, but here I've just written it as one. And then there will be some number of hidden variables that we don't particularly care about because we can't really observe them. Remember, like in our auto insurance model, there were certain variables that we weren't allowed to ask people because we don't want to discriminate against them, and then there were certain other variables that we can't ask them because we know they're just going to lie to us about, like, are they a good driver? So these will be hidden variables, and what we want is to ask questions like, of the model so that it can predict these query variables given the evidence, and we just don't care about the hidden variables. So this is what we want, P of Q given all the evidence. And the way that we do this is we look at our big joint distribution, and we cross out all the entries in this table that are not consistent with the evidence that we've provided, right? So we just collect all of the entries in the table that are consistent with the evidence, and then we sum out all of the hidden variables that we don't care about. And then when we get to the end, so that looks like this, right? Summing up all of the, so when we take those entries in the table, those will be all the ones that are consistent with the evidence, but they'll have lots of hidden variables still. So we're going to sum out all the hidden variables. And when we're done, we're going to be left with another distribution that we then need to normalize so that it sums to 1. And that's this last piece. So we've done this a few times. This is sort of like what we were practicing last time when we had like a big joint distribution and we wanted a conditional distribution, or we had a big joint distribution and we wanted a smaller joint distribution that gets rid of certain variables. So that's called a marginal. So hopefully this should all be somewhat familiar to you all by now. And the basic idea is we take our big joint distribution and we do this process, and then we can get our answer. But of course, we have Bayes nets now, so we don't need to worry about our big joint distribution. We can use our sort of Bayes net structure to encode the joint distribution as this product of conditional probability tables. And this can potentially help us simplify the computations a little bit. Right? So if we have this query, remember this example from last time, this was like the alarm network, right? So there's 2 reasons my alarm can go off. One is that there was a burglar, B. One is that there was an earthquake, E. And then because I'm not home, I need John or Mary to call me whenever my alarm goes off. So in this Bayes net, we might want to ask, if John and Mary both call me, what's the probability that there was a burglar, right? Probability that there was, probability that there wasn't. So that's what the plus J means John called me. The plus M means Mary called me. And then the capital B means I want all the possible values of this distribution. So I want to know, was there a burglar? What's the probability? And I want to know, was there no burglar? What's the probability? Okay, so how's this going to work? Well, we know that this is proportional. This is the law of conditional probability. This is proportional to the joint distribution over those 3 variables. And the proportionality constant is going to just be the probability that John and Mary both call me. Okay, so now we have this joint distribution. It's really a joint distribution, but that we've marginalized out 2 of the variables already. So we can think about this as like unmarginalizing this last step here. We want to get this sort of 3 variable joint distribution. We know we have this 5 variable joint distribution that's encoded in our Bayes net, and we're going to marginalize out the E, earthquake, and A alarm variables so that we can get to that joint distribution. So far, so good? Yes, question? What do I mean by what? Yeah, okay, good. So this is saying if I had a big joint distribution over B, E, and A for a particular value of E and A, right? So this is saying this is really 2 numbers. This is the probability of burglar given E plus A minus plus J plus M. Actually, it's 4 numbers. So 1 for each setting of E and A combined. So we'll get 4 numbers times 2 different settings of B. So I guess actually it'll be 8 numbers. So we'll draw the tables out and it'll become a little bit clearer. But so we have this joint distribution that's encoded in our Bayes net. And because we have this Bayes net structure, what we're going to do is we're going to break that up into our conditional probability tables. So each one of these is associated with a conditional probability table. So we have P of B times P of E times P of A given its parents times P of J given its parents times P of M given its parents. Right? So we can always split this up if we just assume that our Bayes net encodes the right conditional probability assumptions, conditional independence assumptions. And now we have this big multiplication here. And that's starting to look scary because there's lots of terms and there's this big summation on the outside over 2 variables. But there's no need to be scared because all we have to do is like split it up. Now this might actually look even scarier. But so all this is it's a sum over 4 terms, right? This terms sort of break here and at the end of the page. So we have one term goes all the way across here, and then we have a second term across the top. So 2 terms on the top and 2 terms on the bottom. Here's term 1, right? This is the term where E is positive and A is positive, right? And then we have a second term, this will be in blue, where E is positive, A is negative, right? So we do all the different combinations of E and A, and then we basically multiply these different conditional probability distributions together for each combination. Okay, so this looks scary, but the nice thing is there's a lot of shared structure, right? So if I compute this yellow piece, I don't have to compute it again, right? And I'm going to see it again. So I get sort of savings. If I can cache the results of my yellow computation, I can save them and use them again when I get to another yellow later. And same for the greens and the blues and the oranges. So that's like the big picture idea of where we're headed. Now you might think, all right, well, why do I have to cache the results? There's only 4 things that I'm adding together. There's only 5 different terms being multiplied together. That's not that big. But let's go back to our car insurance example, and now we have a lot more nodes, right? So if you're multiplying out all of these different distributions together, I don't know, how many nodes is this? It looks like maybe 24. So now you're going to have to multiply 24 things together, and then you're going to have to sum over all the orange variables in order to get your results. So this is going to get really big really quick, and we'll get to how big it gets later. So the core concept is let's try to reuse some of the computations that we've already done. So if you just think about this sort of like sum of products, we have a few different variables here, u, w, y, x, z. I think there's 5 variables. There's 16 multipliers, there's 7 adds. You can go ahead and count them if you don't believe me. So we also notice that there's some shared structure here, right? So there's this xy term, right? There's this. There's another xy over here. So if I compute xy, I shouldn't have to compute xy again, right? And similarly for wy and wy. So a lot of these are like shared computations. If we factor this, then we can do it in 2 multiplies and 3 adds, right? There's an add for each term, and then there's a multiply for each of the pairs of terms. So this could be like pretty great savings. And the thing to recognize here is that when we go back to this kind of expression where we're sort of enumerating all the variables, this is the same kind of thing. It's a sum over a bunch of products, right? It's a sum over E and A of a product of a B term, an E term, an A term, a J term, and an M term. So if we can figure out the right way of factoring this expression, if we do the multiplies in the right way around the additions, then we could save ourselves a lot of work. So the key idea is to notice that P of B doesn't depend on E or A. So we can pull it out of the summation, right? So we can pull this P of B from here out of the summation and put it in the front. And similarly, P of E doesn't depend on A. So we can pull that out of the A summation. And so we have sort of a choice here of which one we want to push in further. But we have these 2 summations, one's over E, one's over A, and we can look at all the terms that do or don't depend on those variables, and we can push the summations in as far as possible. Then what we're going to do is we're going to do the calculation from the inside out. So we start with the A, we multiply all the A terms together, we get some sort of distribution, then we sum out the A, and then we multiply whatever that is by P of E, sum out the E, and hopefully this is going to compress the work so that we're sort of doing this. We multiply 2 distributions together, we squeeze out 1 variable, we multiply a couple more, we squeeze out another variable. And so this is hopefully going to save us some computations by doing them in a reasonable order. So here we're summing over A first, and then we're summing over E. We could do it in the reverse order. We'll get sort of into how to choose what the right order might be later. Okay. So one thing to note here is that this P of A given B, E, notice that the A's and the E's are lowercase, but the B is a capital letter. So this isn't a single number, this is actually like a table. So you can think of it as an array. This is just a collection of probability values. So we're going to have to do some array multiplies and some array adds, but that's no problem. We know how to do those things. So just something to keep in mind. Whenever we see a capital letter, it means all the different variables that, all the different values that that variable can take on. And whenever we see a lowercase letter, it means we've defined it to be specifically this lowercase letter, this particular value of that variable. Okay. Questions so far? Big picture stuff? Nice. All right. So inference by enumeration is sort of the method where we do this, right? We multiply all of the conditional probability tables together. We get this giant unwieldy joint distribution that's like a function of all the different variables. And then we're going to start summing out all the variables we don't need. By contrast, this variable elimination strategy is saying we're going to eliminate all the variables that we don't need the minute we realize we don't need them anymore. So we're going to multiply two distributions together, and then immediately, if there's any variables we don't need anymore, we're going to sum them out. And then once we've summed them out, we can try multiplying the result by any distributions that we still need to multiply in. Then we're going to sum out all the stuff we don't need, and we're going to keep repeating this process. So we're always summing stuff out as soon as we can sum it out. Okay? So variable elimination is going to be a lot faster than inference by enumeration because we don't need to compute this big exponentially large joint distribution. We can kind of go along in this linear fashion for a lot of practical problems. It turns out that it's still going to be exponential in the worst case, but it's much faster in practice. And so we'll see kind of some speed ups there. So in order to do this, we're going to need some new machinery, and that machinery is called factors. And in order to learn about factors, we're going to have to take a trip to the factor zoo. So this is today's code that will let you into the factor zoo. Everyone, please enter this code to your to the scanner, and then we'll take a trip and we'll look at what some of these factors might be. Okay, good to go? Right, so the first thing in this factor zoo, remember a factor is it's the name for one of these probability tables. Once we multiply a couple of things together, we're going to call that a factor. One thing that we might find is a factor that has two capital letters in it. So P of x comma y, where x and y are capital letters. And so what we said before is that like whenever these letters are capitalized, it means I want to think about all the different values that x can take on and all the different values that y can take on. Right? So this is a joint distribution. It's the same type of joint distribution that we know and love. We're just going to call it a type of factor now. We have entries for all the different x's and all the different y's, and they all sum to 1 because it's a joint distribution. Okay? So that looks like this. So if we have this temperature and weather scenario, right, the temperature can be hot or cold. Those are the only two temperatures. And the weather can be sunny or rainy. Those are the only two types of weather we have. We might get a joint distribution that looks like this, right? So 0.4, it's hot and sunny. 0.1, it's hot and rainy, etc. Okay, so that's one type of factor in our factor zoo. Another type of factor is a lowercase letter followed by a capital letter. And what this means is the lowercase letter, we want a particular value of x, and we want all the values of y. So in the same situation, we would have cold would be the particular temperature that we're looking at, and we still want to know all the different types of weather. So sun and rain, again, those are the only two types of weather. So we have this table, and notice that this table is just a slice of this table. It's the bottom row, okay? So this is a selected joint distribution, or a projected joint distribution, sometimes you'll see. And it has entries for x and y for the single value of x that we asked for, and all the values of y. And what does it sum to? It doesn't sum to 1 anymore. It sums to P of x. This is like the probability that it was cold, right? So it sums to 0.5 because there's 0.5 probability that it was cold. Okay, so that's the second type of factor. Questions so far? There's 3 more types of factors we're going to see. Yes? Yeah, it's just we need a name for these tables that we're multiplying, and so we're calling them factors. Yeah, exactly. Other questions? Okay. Factor, oh, yeah, one more thing. So I think I mentioned this already, but the number of capitals is going to tell you the dimensionality of the table, right? So if I see 2 capital letters, X and Y, that's a 2 by 2 table. It's 2-dimensional. If I see 1 capital letter, P of X comma capital Y, we get rid of this dimension, the temperature dimension, and we only have this sort of weather dimension now. So it's a 1-dimensional table. Okay. So the number of capitals tells you the dimensionality, which is kind of helpful. All right, factor number 3. This is a single conditional distribution. We saw a bunch of these last time. So this is saying when I have a particular evidence variable, x, I set it to that value, and then I want to know what are the probabilities of all the different variable values for y. So this will look like this. So I'm saying conditioned on the temperature being cold, what are the possible weather values? So this could be like 0.4 and 0.6. Notice that now this is a proper probability distribution. It's normalized to 1. So this is kind of similar to the one we just saw where it's a slice, but now we've divided that slice by whatever normalizer we need in order to get these things to sum to 1. Yes?
It's the same as what we saw last time with the alarm and those things, right? It's not a new...
This is just a conditional probability distribution, yeah, but this is one of the types of factors that we might see inside of one of these variable elimination procedures, yeah. Okay, other questions? Yes? How do you define what's a capital and what's not? Yeah, good. So that's going to be defined based on what type of question you're trying to ask your probability model. So if you're saying, I want to know, what's the probability over all the weather types that I might see, right? I want to know the probability for sun and the probability for rain, conditioned on knowing a bunch of stuff. Like I know that it's hot. If I know that it's hot, then the temperature variable is going to be lowercase. But if I want all the different types of weather, the weather variable is going to be uppercase. And then if there could be other variables in there. It could be like there's a traffic variable or something, right? Like we had traffic last time. So if the variable doesn't appear, we want to sum it out. So it's not going to show up in our final calculation. Thanks for the question. Other questions? Okay. Here's another factor. This is a family of conditionals. So now we make y uppercase. Actually, we make x uppercase. And this is just like we had before. In fact, we're going to see that in this table, we're going to get this table as like a slice of this table. So this is saying it's multiple conditionals. We have all the probabilities of y given x for all the different values of y and all the different values of x. And each one of these rows is equivalent to a conditional distribution for a fixed temperature, for a fixed x. So each one of these rows is going to sum to 1, and then the total probability in the table is going to be 1 times the number of possible 1 times the number of possible conditioning variables, x. Okay? So this is whenever we see a conditional that has a capital letter followed by another capital letter. Yes? Why do we have 2 different types of what? Oh, this is just page 2 of the factor zoo. Yeah. Yeah. Okay. Other questions so far? We have one more type that we're going to talk about. Yeah.
So this is just like the original table, but each column is normalized to 1?
This is just like which table?
The original table.
The joint distribution? Yeah, so this is like the joint distribution, but each row is normalized to 1. I think that's correct, yeah. I mean, we can go back and check, right? So what was our original distribution? So we had 0.4, 0.1, 0.2, 0.3. Okay? And then if we go over here, now we have, it was 0.4, 0.1, so we've multiplied that by 2, that sums to 1. And then 0.2, 0.3, that also sums to 1. So yeah, so we've divided each one so that it sums to 1. Yep. Okay. More questions? Yes?
Can you explain what is the number of capital again?
Yeah, so we have some letters. Is my pointer working here? Okay, so we have y and we have x, right? Y is capitalized and x is not. So the number of capitals in this expression is 1, just for y. Down here we have y and x. They're both capitalized, so that's 2 capitals. So notice when there's 1 capital, we have a one-dimensional table. It says we have one row and it's this many wide, right? So this is just a vector, basically. Whereas when we have 2 capitals, it's a 2-dimensional table. If we had a joint distribution over 3 variables or a conditional distribution over 3 variables, and all of them were capitalized, we would have a 3-dimensional table. We'll see one of those in a sec. Okay. Here's the last type of factor that it might be worth specifying here. So we have a lowercase letter conditioned on an uppercase letter. You can probably see where we're going with this. It's going to be, so first of all, there's 1 capital letter, so it should be a vector. It should be a one-dimensional table. And what this is going to say, we want an entry for each y conditioned on x for all the values of x and a particular value of y. So that looks like this. It's like the probability of rain conditioned on each possible temperature. There's 2 possible temperatures, hot and cold. This doesn't necessarily have to sum to 1. We don't necessarily know what it's going to sum to. But it's a type of factor that we might see, so we put it in there. Okay? All right, so those are the types of factors. And in general, a factor is a table, right? It's a table of probabilities. And we might write it this way that we've been seeing, right? P of A, B, C, D. Or we might just say it's a factor and it has these variables in it. Either way, it doesn't really matter. These are just 2 different names for the same thing. All we want to do is keep track of what are all these probabilities that we're multiplying together and what is the shape of this table so that we don't lose track of anything. Okay? So it's just a multi-dimensional array. The dimensionality is determined by the number of capital letters. The sizes of each dimension are determined by the number of values in the capital letter. And we're sort of off to the races. This is what we mean when we say factors. Questions on this? Okay, great. Let's do a practice problem. So the traffic domain now is that there's a raining variable. Raining influences whether there's traffic. Traffic influences whether I'm late for class. Okay? So ideally, we don't want to be late for class. How are we gonna think about this? So we have 3 different random variables. This is the structure of our Bayes net. Raining, traffic, late. They sort of depend on each other in this way. And this is just the structure piece, right? The Bayes net is not complete yet. We need to have these conditional probability tables. We need to know the probability of R, we need to know the probability of traffic given rain, and we need to know the probability that I'm late for class given that there's traffic, okay? And you can debate whether any of these values are actually correct, but this is just how we'll say that we're going to do it for now. So we want to know, like, what's the probability that I'm late for class? Okay? So, well, we know that the probability that I'm late for class is the joint distribution over rain and traffic and being late for class if I were to then sum out all the different possible values of rain and traffic. So this is like marginalization. We can take a joint distribution and go to a marginal by summing out the variables we don't care about. Then we can use our Bayes net to split this joint distribution up into those conditional probability tables. And each one of these should look like one of the types of factors that we just saw. And so our initial factors will just be the conditional probability tables from our Bayes net. Okay? So we're going to work our way up to this idea of variable elimination, which is the one where we're going to eliminate variables as we go. And we're going to start with a simple like inference by enumeration, do it the sort of the hard way, and show what that looks like. So we're going to track these objects called factors. each of the conditional probability tables will be our initial factors. And so these are our initial factors, right? We have one for rain, we have one for traffic, we have one for being late for class. We start by saying any known values, like if we know that we're late, we can just select those rows from the tables and not worry about the other rows, okay? So if we know what the initial factors are, then if we know what the evidence is for a particular variable, then we go through and we say, okay, basically we're going to set these tables and we're going to throw out all the rows that we don't care about. So we only care about being late for class. We don't care about not being late for class anymore. Just select those rows, okay? Then the procedure is we just join all the factors together, we multiply them all together, and then eliminate all the hidden variables, and then normalize so it all sums to 1, and then we're done. Okay, so the first step is we are going to multiply things together. This is joining factors. And this is like essentially a database join if you've seen databases before, or you can think of it as like a point-wise product between two different matrices. Here's what that looks like. So we have two different tables. We want to join them together. We have a factor for R and we have a factor for T with R. Okay? So joining these together is going to look like producing a joint distribution over R and T. Okay, and so how are we going to fill in the entries of this table? First of all, we have two capital letters, so how many dimensions is this table going to be? 2. Great. And what are the sizes of those two different dimensions? What's the size of the R dimension? How many possible types of events are there for the rain variable? 2. It's either raining or it's not. Okay, what about the temperature variable? How many temperatures are there? There's only 2 temperatures. There's hot and there's cold. Right. That's good. Okay, so this should be a 2 by 2 matrix. And how are we going to compute the values in this 2 by 2 matrix? Let's say, what's the value of the rain is true, or temperature is hot cell of this 2 by 2 matrix? How do I compute that? What do we think? Does anyone have ideas of how we could compute the probability that rain is true and temperature is hot? Yeah.
Can you just multiply the probability rain's true and the probability that is hot given rain's true?
Yeah, so the first entry in each table, right? So probability that rain is true times the probability it's hot given that rain is true. So that's 0.1 times 0.8 is 0.08. Yeah, we can do that. So we're essentially going to take a pointwise product. We're going to match the variables that are in both tables, and then we're going to look at all the different combinations of the variables that are in only one table. And that gives us our 0.08, and it gives us all these other things. We're just basically multiplying this number in this table by the associated numbers in these tables in order to get this table. Does that make sense? Everyone see how that's working? Okay, nice. So what have we done here? We've taken this Bayes-net that goes from R to T, and we've essentially collapsed it by multiplying factors together into a new Bayes-net that's a joint distribution over R and T. So R and T, the combined joint variable you can think of, has 4 different values, and those are rainy hot, rainy cold, sunny hot, sunny cold. So this is a new variable, R comma T. It's the only node in this Bayes-net, and it contains those 2 variables that take on 4 values. So that's essentially what we've done. Okay, so we can actually continue. We can join things together multiple times. We can do one join followed by another join, and we can get a 3-dimensional probability table. Right, so we start in the same situation. We have R, T given R, and L given T. We join R. This looks like just what we did before, right? We get our joint distribution over R and T. We sort of bring this one forwards, and now we're going to try and join this RT node, which is now pointing to L. We're going to join on T. So this works exactly the same way. It's going to give us a distribution over R, T, and L. So how many dimensions is our table now? 3, because we have 3 capital letters. Okay, and what are the sizes of those dimensions? 2, 2, and 2. Okay, yeah, good. So we've just drawn it as a vector, but you can think of this as being 2 by 2 by 2. And the probabilities in this matrix, they're coming from just multiplying these probabilities together. So there's 4 values in this table. There's 4 values in this table. How do we get these values here? Well, this one here is the probability that rain is true and temperature is hot and I'm late for class. And so what we have to do to get that value is we look at the probability that rain is true and temperature is hot and temperature is hot and I'm late for class. We multiply those 2 things together and that gives us this 0.024. Okay, so then that's how we would do that. I won't go through the rest of them, but you can sort of check for yourselves that those numbers come out right. And notice that they sum to 1 because this is a proper joint distribution. Okay, questions on this? So multiple joins, does that make sense? All right, nice. So the Bayes net is going to collapse these 2 terms together, and now we're going to get a Bayes net that's over a triple variable, right? An RTL triple. And so each of the values that this triple can take on are sort of the values that we see in this table, plus, 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 minus, etc. So we've gone from this 3-node Bayes net over 1 variable each to a much bigger table over 3 variables that are all combined into one joint distribution. Okay, that's joining things together. That was step 1 of this inference by enumeration process. We've now enumerated our whole joint distribution. And now we need to eliminate the variables that we don't need anymore. So these are all the hidden variables we didn't ask about, right? So if we go back to the 2-dimensional case, we might have this P of R given P of R and T joint distribution. We might say, all right, I only care about the temperature, so I'm going to sum out the R variable, and I'm going to get a distribution over T, and that looks like this. And it's going to have 2 entries, 1 for each temperature. And I've basically, what we've done is I've summed all of the values in this first table that correspond to, let's say, T equals hot, right? So T equals hot, there's a 0.08 here. T equals hot, there's a 0.09. Those sum together, and we get 0.17. Okay, questions? Yes?
Once you came up with that big distribution table, is there any more purpose in the Bayes net and its structure, or can you just get everything from the table?
So once you have this big table, do we need the Bayes net? No. I mean, if you can fit that whole the whole joint distribution into memory and your computer doesn't explode, you can totally do it that way, and this will work. But for a lot of these problems, you're going to find that that's actually quite hard to do because the joint distribution blows up, it's exponential, and then your computer crashes, and it's not fun. So yeah, if you can get away with it, writing down the joint distribution is totally fine. And if you can't get away with it, you might need smaller tables, and you can fit smaller tables if you have n different conditional distributions rather than one 2 to the n size joint distribution. Thanks for the question. Other questions? Okay, great. We can also eliminate multiple variables at once. So if we have this 3-dimensional distribution, R, T, and L, we might say, all right, I would like to sum out R. No problem. So we just have to identify, let's say we're going to sum out the R equals positive case first, right? All the ones where it's raining. So we sum all these things together, and we get 0.051. No, that's not right. Hold on. So we're summing out all the, so I've messed this up actually. So, right, so first of all, what's the shape of our table going to be? It's going to be a TL thing, and it's going to be a joint distribution over T and L. And so for each node in this table, we have a plus, oh, where's the pen? We have a plus T and a plus L. So what we have to sum over is all the ones where plus T and plus L appears. So it's these 2. So we have a 0.024 and a 0.027, and we get a 0.051. And then similarly for down here, now we have a minus t and a plus L. I'll do that in red, minus t plus L. So we have minus t plus L and minus t plus L. And so we have to sum 0.081 and 0.002, and we get 0.083. So now we have this joint distribution over t and L. And we said we're trying to do multiple eliminations, so let's sum out something else. Let's sum out t. So now we should get a distribution over L. It should have 2 entries, and those entries will be these 2 entries. So all the ones where L are positive, those are the 2 that I circled, those will sum to 0.134, and the other ones will sum to 0.886. Making sense? We're just doing the same step twice, right? So we start by multiplying everything together. We get this 3-dimensional looking box thing, and then we're going to clamp these 3 dimensionals into 2, and then we clamp the 2 dimensions into 1, and then we're back to where we need to be. So this is how we answer the question of, am I going to be late for class? What's the probability of being late for class using this particular Bayes net if we want to do inference by enumeration? Yes?
Could you do like both steps in one?
Can you do both steps in one?
Yeah.
It's like sum over both variables at the same time?
Yeah.
Well, so let's go back a second. So I think that's what I was trying to do, and that's why I got hung up a little bit. So what we have to look at is, like, for each combination of t and L, we need a sum over R. So I guess we could look at so maybe we could do it like this, right? So if you wanted to go in 2 steps, let's say you want to just compute, I'll do it in purple, okay? Let's say you want to compute this term right here. So which terms would you have to look at in this table in order to get that? You would have to look at all the ones with the plus L on them. So that's this one, and this one, and this one, and this one. And lo and behold, those are all the ones that we looked at. So yeah, so you can do 2 at once if you want. Other questions? Yes? Is there a mistake somewhere? In the PL table, it should be 0.866. I think you might be right. Yeah, I think that's right. We'll have to fix that. Okay? Thank you for that. So, oops, think of this as 0.866. Great. Other questions, comments, other problems with the slides? Yes?
So would this pattern of like joining and summing work for like higher and higher dimensions?
So it depends on how big your computer's memory is, right? Higher and higher dimensions means that, like, you're going to have a bigger and bigger exponentially sized joint distribution. And instead of a 3-dimensional box, you're going to have an n-dimensional distribution that you have to worry about. It's going to be really big. And then if you can afford it, you can totally do that. Okay, so yeah, this is the process where we take multiple joins and then we do multiple clamps, right? Multiple summings. And what we're going to do instead now is we say, okay, my computer's not big enough for that. I can't afford to put these whole joint distributions into memory. So now I want to do things more efficiently. I want to clamp as I go, right? So we take 2 distributions. We realize, you know what? I actually don't need one of the variables. We clamp them together. We get this purple guy. We multiply that by the green guy. And then we have this distribution. Now we realize we only need one of them again, and so we clamp it, right? Clamping as we go, marginalizing early. This is variable elimination, eliminating variables as we go. So we have our 3 different conditional tables again. We're going to join the R variables. So that gives us this situation, right? Same as before, we have RT going to L. And now we say, okay, well, I no longer need R in order to join these 2 tables together. So I'm going to sum out R. And what summing out R is going to do is it's going to give me this situation where now I just have T. T has an arrow going to L, and now I have T and LT. I can join on T, right? So when I do that, my table down here is not going to get larger. It's just that the numbers are going to be multiplied by these things. So now I have T and L, and I don't have to have a 3-dimensional table anymore. The RTL is gone. So just T and L. And then we can sum out T, and we get this distribution over L. And notice that we get the same answer here. And actually, for some reason, this one has 0.866, so that's nice. So someone fixed this slide, but not the last slide. So we can do this in either order, but this one, we didn't have to build our whole big joint distribution, and now we're happy about that. Okay, questions on this? All right, great. Let's talk about evidence. So what do I mean when I say evidence? I mean, we know certain things about certain variables, and we want to leverage that to make these computations more accurate and more efficient, right? So if we start with some evidence, then we don't need to look at other aspects of these tables that are inconsistent with the evidence we already know, right? So when we know some evidence, just select those rows. So if there's no evidence, we just use the same conditional probability tables we started with. But let's say that we know that it's raining, right? At the time that this thing crashed through the wall, it was raining, right? And he was wondering whether he was going to be late to class. So we know that it's raining, and so we say, okay, well, there's a plus r here. We don't care about the minus r. There's 2 plus r's here. We don't care about the minus r's. So we can simplify these tables. This one doesn't have any r's in it, so we can't simplify anything. So we're just selecting rows from these tables that are consistent with the evidence we've seen so far, and that shrinks our factors before we even have to multiply them together. So this saves us some work. Right? Eliminate all the variables other than the query and the evidence. Those are all the hidden variables, and we're sort of doing the same process as before. Right? So P of L, given that it's raining, this is how often am I late for class given that it's raining, we end up with these factors. These are the ones over plus L. And we just normalize this in order to get our answer, right? So we normalize that, and now we have a sort of a quarter likelihood that I'm late for class. That's it. It's like really simple. So there's just like this one extra step where we normalize at the end because we've selected some different pieces of the evidence in the first place. Okay? Yes? The thing that's going to save you the most memory is using a Bayes-net in the first place instead of a joint distribution. And then when you're doing the inference step, not multiplying everything together before you start doing this summing out. You want to sum as you go. That's what's going to save you the memory. But yeah, this is also going to save you memory because now you're no longer looking at, I mean, your product is going to be smaller if you get rid of certain entries in your tables as you initialize, because you no longer have to worry about rain being false. So instead of 4 entries in this table, you're going to have 2 entries in this table. Okay, so here's the general view of it, right? So we have some query variable or multiple query variables. We have a bunch of evidence variables, these E's, E1 through K. And we might have some hidden variables that we don't necessarily care about. We will initialize everything with our local conditional probability tables. We'll instantiate that by the evidence. So if there's any evidence rows that are not consistent with the evidence that we have, we're going to just push those out of our tables. Our tables are going to be these compressed things. We multiply them together, but we only multiply them together as needed. And then as soon as we can start summing variables out, we do that along the way and eliminate variables as we go. Okay? That's going to give us the sort of the most efficient route to a final answer. And then when we get to here, we just have to make sure that we normalize so that the last thing sums to 1, and then we're good to go. Okay? So let's try that on this alarm network example. So we won't go through the individual probabilities anymore. We're just going to do it in symbols now. So we have all these different initial factors. These are just the same conditional probability tables from our Bayes-net. Those are our initial factors. And we want to know what's the probability that there was or wasn't a burglar given that John calls and Mary calls. Okay? We know that's going to be proportional to this joint distribution over burglar, John, and Mary. And the proportionality constant is just the probability that John and Mary called. So we have these 5 different factors. Right, so we have 2 hidden variables here, E, the earthquake, and A, the alarm. And we have a choice. We can decide whether we want to marginalize out the earthquake variable first, or we want to marginalize out the alarm variable first. And let's just say that we choose A, right? We choose A, so then these factors involve A. We want to multiply all the factors that involve A together, and then we want to sum out A. So first we multiply. We get this thing. It's P of J, M, capital A, given capital B, capital E. This is just a factor. Don't need to really interpret it so much, but that's like, it's a joint distribution over 3 variables conditioned on 2 other variables. And the capitals means we want all the terms, and the lowercase means we want the specific terms. Okay, so we multiply those together, we get this factor. We then sum out A, because these are all the terms that have A in it. So we are ready to sum out A. We don't need A anymore. We sum A out. We get P of JM given BE. Okay? And now our factors are PB, PE, and P of JM given BE. Now we choose E. Okay? And so we take those factors, we multiply the ones that involve E together. We get JME given B. We sum out E. We get P of JM given B. And then our remaining factors are whatever we didn't use so far. So this PB will come down, and this P of JM given B will come down. We have 2 factors remaining. We're just going to finish with B. We're going to multiply these 2 factors together, and then we're going to normalize, and what's remaining is a distribution over B conditioned on JM. Okay, I went through that kind of fast, so let's see the exact same thing again, but we'll just put all the equations on one slide. Okay, so we start with our conditional probability tables, BE, A given BE, J given A, M given A. We know that we want B given JM. That's proportional to this thing. This thing can be written as a marginal of the full joint distribution over all 5 variables, so we write it this way. And then we use our Bayes-Net structure and the conditional probability tables to write that in a succinct way. We have this E and A as a summation on the outside. We're going to push in either one of those variables as far as it will go and pull all the stuff that doesn't depend on that variable out. We just happen to choose A first, so we push A in. We get to here, all these terms depend on A. Now we can sum out A. So we multiply these terms together. We get our sort of factor F1 and sum out A. That's F1. Okay? So we've just named it F1. There's no reason why it has to have this name, but it's a factor. It's the first one we've computed, so we call it F1. And then from there, we say, okay, now we have this other variable E. We don't care about that variable either, so we're going to push the E summation in as far as it will go. That pulls the P of B out. We have 2 terms with an E in them. Multiply P of E times F1, sum out over E, and we get another factor. We'll call that F2, sort of an arbitrary name. Right, so now we have P of B times F2 of BJM. So we can then join these on B and then normalize, and that'll give us our result, just the same as before. Yes? From this one to here? Okay, great. Yeah, that's a good question. So the question is, how do we go from this joint distribution over all 5 variables to this product of conditional distributions? There's 5 different conditional distributions. The answer is, we looked at our Bayes-Net, and we said a Bayes-Net is a way of encoding a joint distribution over these 5 variables. And the structure of the Bayes-Net tells us that B doesn't depend on anything, so we have a P of B. E doesn't depend on anything, so it's P of E. A has 2 parents, B and E, so A has a conditional distribution, A conditioned on BE, that's this guy, or this guy. And then we have J given A and M given A, and those are the last 2 terms. Yeah? Why is B capitalized? So when we see a capital letter, that just means we want all of the possible settings of B. So this is this saying, I want to know what's the probability that there was a burglary and what's the probability that there was not a burglary. Okay? You're welcome. Any other questions? Yes?
So with that, when you say E, does it mean that we need it to be the earthquake?
So that's a good distinction, right? So when we see a lowercase letter, if there's a summation, it still means like we care about one value at a time, but we're also sort of summing over all the values, right? So here, this thing is a table that's 2 by 2 by 2. But when we get down to here, each entry in this summation just has one value of earthquake, just has one value of alarm, because that's why they're lowercase. So it's just a way of keeping track of what are we doing here. So this is saying I want all the values of E and all the values of A. This is a summation over a summation of this probability. Okay, other questions? Yes? What is the form of F1? That's a great question. Okay, well, let's look. So we have P of A given capital B, lowercase e, times P of J given A, times P of M given A, right? So let me make this a little bigger so that I can write on it. So we're looking at this, right? So what will be the form of F1? Well, first we have to multiply these things together. So we have P of, put all the things on the left, A, comma, J, comma, M. Okay, given all the things that are only appearing on the right, given B, E. Okay, and then we're summing out A. So we get rid of this. So this will be P of J, M, given B, E. So the form of this thing is this. Okay? It's actually not important for us so much what the form of these intermediate factors are, and that's why when we write them as these F notations, we sometimes just ignore the conditional, but we can write them either way. Thanks for that question. Does that make sense? Folks see how I did that? Yes?
If we don't know exactly what the factor is, how do we calculate the end results if we don't know what the factor is?
If we don't know what the factor is, how do we calculate the end results? What do you mean we don't know what the factor is?
I guess like for F2,
Yeah.
we don't know exactly if that's like conditional or if that's a multiple. So what do we do with the table there? Do we just have the table and just use that as a calculation?
Well, so yeah, so we still know sort of what names are associated with which dimensions. So when we have a factor that has these dimensions and one of them matches to this table, we say this table has a B in it, that table has a B in it, we're going to join them on the B. So that means whenever I see a plus B over here, I look for the plus B terms over here, and then I do my sort of join type pointwise product thing. So as long as you know which dimensions are which, and we always will, then you can do these calculations and you'll be okay. You don't have to keep track of what the conditional placement is. Yeah. Why do we go from F1 to F2? So we're going from this summation over E times of P of E times F1. That whole thing, that summation is going to F2. So it's not that we're going from necessarily this factor. This is just a name for some table that we found in the process. And then this is a name for another table once we've multiplied those two things together and summed over E. So we've just named that a different thing because it's a different table. Okay, good question. Other questions? Okay, nice. So the order, we said we could do E first or we could do A first. We chose to do A first. The order turns out to matter quite a lot. So if we have this model, this is what we called a naive Bayes model last time. We'll talk about that more a few times in this class. If we have this model, and let's say that we want the probability of D, right? For whatever reason we want the probability of D. Well, there's a couple of choices for orderings that we can do. If we order the terms Z, A, B, C, D, and then we sort of do them in this order inside out, then this D term will appear last, then we'll have C, we can sum out over C, sum out over B, sum out over A, and then we sum out over Z last. Okay, so if we do things in that order, then we have a term that's 2 entries by 1 times a term that's 1 entry by 1. And then we sum out all the values of C. So the maximum size of this resulting product is 2. And we have the same situation again. And it's a 2-variable table, and then a 2-variable table, and then finally there's another 2-variable table that we sum out over Z, and then we get our probability of D. So if we go in that order, the largest factor has 2 variables. If instead we order the terms like this and we try and do the sum over Z first, we push Z all the way in, then we have all 5 terms to multiply. we multiply them all together, and then we sum over z, and then we get a table that's got A, B, C, and D remaining. We've essentially got rid of this node and collapsed all 4 of these nodes into a joint distribution over A, B, C, and D. And this will essentially look like inference by enumeration. We will have built our entire joint distribution first, our computer will have crashed, and then we're going to try and take some sums out of the remaining thing there. So in general, if we have n leaves and we do it the wrong direction, if we take the parent first, then we're going to get 2 to the n sized factors, whereas if we go in from the leaves first, then we're going to get like linear in the size of the factors. So 2 variables. 2 versus 2 to the n. I mean, which one do you want to pick? Let's say that you had a bigger network, right? We'll go back to our insurance example from last time. If this is the network, if you want to do the whole joint distribution, you're going to be looking at like some 20-ish dimensional joint distribution, and many of these variables have lots more than 2 possible values associated with them. If you were going to go the sort of full enumeration route, you'd look at 200 million operations. If you do this in a clever way and you do the variable elimination, where you're eliminating variables as you go, you get a 1,000-fold speed up. So that's really nice. So we can talk about the computational and space complexity of variable elimination. It's determined by the largest factor. And basically, it's the space that's going to kill you here, right? So your computer's going to run out of memory long before you get tired of waiting. So we talked about how the elimination ordering can really affect the size of this largest factor. If you pick the wrong ordering, it can lead to this sort of exponential blowup. We saw that with the ZABCD example. And the question is like, well, okay, why can't we just always pick a good ordering? Then we should be good to go, right? If we always pick a good ordering, then we should be happy. And the answer is that we can't always do that. It turns out that you can show that in the worst case, this is like NP complete. It's NP hard. And I'm going to try to prove that to you using this technique called reductions. Who's heard of reductions before? Okay, a couple people. This is sort of like something that you'll hear about in like 170. If you take 170, it's like a computational complexity idea. Very simple, but it can tend to be a little bit confusing. So if I have a problem that I know is hard, and we know that SAT is hard. We know that SAT is one of those like classic NP-complete problems. It's something that's like as hard as any other problem that's in this complexity class called NP-complete. Not important what that complexity class is, we just know that those things are hard. Traveling salesman problem is hard, set cover is hard, there's a bunch of other NP-complete problems. We know SAT is one of them. So if we know SAT is hard, and we want to know, is variable elimination hard? How can we use our knowledge of SAT to help us determine whether variable elimination is hard? Well, we know SAT is hard, so imagine that we could solve SAT using variable elimination. So we're going to try to reduce SAT into variable elimination. If we can say there is some reduction that goes from SAT to variable elimination, and I have a fast variable elimination algorithm, like the submodule that I can run, then I can use my submodule to solve the variable elimination problem, and then I can tell you the answer to your SAT problem using my variable elimination solution. So we're using one program inside of another program to make that first program run faster. So if we know that SAT is hard, and we can show that there's an efficient reduction from SAT into some other problem, then we know that that other problem has to also be hard. Otherwise, this problem that we know is hard is actually easy, and then we get to publish like some really groundbreaking papers because the whole field of complexity theory will have a field day. So that's the strategy. We want to show, can I take an instance of SAT and turn it into variable elimination? And if I can do that in polynomial time, then I can prove to you that variable elimination must be hard. Otherwise, I'd be able to solve SAT quickly. So SAT has some variables. We're going to encode those into our BaseNet as nodes, W, X, Y, and Z. Can ignore the probabilities on those nodes for now, but there's a reason why they should be a half. And then you have some clauses. These are conjunctive normal form clauses, right? So we have some clauses, W or X or Y or Z or not W, etc. We have these clauses, and then we want to encode those clauses as additional nodes in the BaseNet. And so each one of these clauses is going to be associated with a conditional probability table. So we can say that, like, let's look at this one for C2, okay? So C2 is going to have some probability of C2 conditioned on W and Y and Z. So we need to come up with a probability distribution that encodes the clause that we have for C2. And so the clause says C2 is true whenever Y or Z or not W is true. Okay? So if Y is true, or Z is true or not W. So let's say 0, 0, 0. We have not W, so that means yes. So we have a probability on C2 of 1 whenever we have that condition, right? And then we go to the next one. We say 0, 0, 1. We basically build up our truth table, and then we're essentially saying we want our probability distribution for this conditional probability table to reflect the truth table that's associated with that particular clause. So now we look at Z equals 1 and W equals 0. Well, W is still 0, right? And so not W is going to say yes. So there's a bunch of other things here. Eventually we get to this one, right? And so we have Y or Z or not W, and so there's going to be a couple of zeros in here, but overall it's going to be a lot of ones. Okay, so this is our conditional probability table. It's saying C2 conditioned on all of these things. And then we're going to have another conditional probability table for each of C1 and C3. And then we need a sentence. This is like the thing that we want to know if this can be satisfied, right? So in a SAT problem, we have a sentence. It's an and of a bunch of clauses. Each clause is an or of a bunch of propositions. Those can be positive or negative. And so this final sentence, we just need one more node, and this we need to encode with another truth table probability distribution, which says, you know, given C1, C2, C3, and I want to know S, basically 0, 0, 0, nope, 0, 0, 1, nope, dot, 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 and then we get 1, 1, 1, that's our only yes. So the only time that this thing is true is when we have all the different clauses. So we can build up a conditional probability table for the S node as well, and that allows us to essentially ask one question of our BaseNet. We have to do one inference in order to figure out if this SAT problem can be solved. And that question is, we just answer this. Is P of S greater than 0? If P of S equals 0, it means no setting of W and X and Y and Z causes this sentence to be true. But if P of S is greater than 0, then some setting does. There might not be that many settings. It might be kind of hard to find that setting, but we don't care about finding it. We just want to know, is it satisfiable? And if it's satisfiable, then we can solve SAT using this. Well, I didn't prove to you that this took polynomial time, but you can trust me on that part. You can get a polynomial time reduction from SAT into a BaseNet that you can run variable elimination on, and then you can get this result in a polynomial amount of time. Therefore, it is an NP hard problem to run variable elimination. Turns out it's actually worse. There's another complexity class that's even harder called count P hard. Sometimes people call this sharp P hard. And what this is saying is count the number of satisfying assignments to that particular sentence. And because of the way that we set these initial 0.5 probabilities, each combination of W and X and Y and Z is 0.5 raised to the n likely to occur. So each combination of those variables has likelihood 0.5 raised to the n. And so it's true that the probability of the sentence being true is k times 0.5 to the n, where k is the number of satisfying assignments. So we have to ask our network, what's the probability of S being satisfied? And then we just divide by 0.5 to the n, which we can do in polynomial time, and then we get k, and we get k really efficiently if this thing is easy, but it turns out it's not easy because it's actually it's as hard as SAT. So it's not only NP hard, it turns out that it's count P hard or sharp P hard. All right, I won't go into more details on the complexity, but we know that when we have certain types of structure, this structure that we saw before, this is called a polytree, and it turns out that for polytrees, we actually do have efficient variable elimination. So a polytree is a directed graph where if we remove all the arrows and we think about the corresponding undirected graph, that graph has no cycles. So look at these 4 potential graphs and tell me which one of these is not a polytree. So in your head, try and remove the arrows and see if you find any loops. You leave the edges in there. You just take the arrows off of the edges, so they become undirected edges. Any of these have a loop in them? Yeah? Bottom right. Yeah, there's the loop. So if we look at this particular set of edges and we ignore the arrow pointing in the down direction, then we get a loop, right? We could go from the top all the way around back to the top. So that's not a polytree. But the other ones are. They're all directed graphs with no undirected cycles. And so for polytrees, the complexity of variable elimination turns out to be linear in the network size, provided that you pick the right ordering. So if you eliminate variables from the leaf nodes up to, I don't know why the pointer's not working. If you eliminate from the leaf nodes up to, start with these, and then you go up, and then you go up, then it's linear in the network size. Okay? And so for these examples where you have like one node that removing it would cause there to be a polytree, you can imagine that you could like ignore that node. But we can't just ignore the node. What we have to do is consider all the different possible settings of the variable that node represents. So if this is raining, then we have to think about rain and we have to think about sun. And for each of those values, rain, we have a polytree, and then sun, we have a polytree. And so we essentially run the same algorithm. It takes linear time on each polytree. And so if you have a small number of nodes that form what we call a cut set, that's this thing, then you can use this cut set conditioning in order to get these near polytrees to look like polytrees. So this is a type of structure that we can sometimes find, and if we can find it, then we can get some really efficient variable elimination algorithms. So we just solve each polytree separately. Okay, so to summarize, we talked about exact inference. This is saying we have sums of products of conditional probabilities. We want to get the exact answer out of our network, and the way that we do that is with this process of either enumeration, inference by enumeration, which is really slow. We build this big, giant joint distribution, or which is always exponential, or we can move the summations in and sum out the variables we don't care about whenever we don't care about them anymore. This gives us massive speed-ups in practice. It's linear for polytrees, and it saves us a lot of repeated work by caching the results in the meantime. Exact inference is this count P or sharp P hard. The complexity theorists will tell you that it's pronounced sharp P, but the original paper, apparently I'm told, they told you that it's pronounced count P hard. So if you're thinking about going into complexity, just keep that in mind. And next time we will talk about approximate inference when we can't even do any of these things. All right, see you then.